In part B of lecture 3, we start with the proof of 9. Okay, we already proved from 1 to 8 and start with this proof. To prove the relation number 9, we write first the definition of delta. This is given by e to the power half minus e to the power minus half. And squaring both sides, we get delta square. This is given by e plus e inverse minus 2. And the value of I plus delta square by 4, this is given by I plus e inverse minus 2 by 4. And clearly this is 1 by 4 into e plus e inverse plus 2, and this is this is 1 by 4 into e to the power half plus e to the power minus half, and this is half into e to the power half plus e to the power minus half, this is whole square and this square. And this is the definition of averaging operator. This is mu, so this is given by mu square. Okay, and this is the right hand side. So this is the proof of 9. The relation number 10, we already write the definition of delta and mu, and multiplying both of them, mu into delta, clearly it is given by half into e minus e inverse. Okay, and so mu square into delta square is given by, this is 1 by 4 and this is whole square. Now 1 plus this is given by, this is I. This is not 1, this is I. Okay, so we get from here, this is e square, this is minus 2 plus e to the power minus 2 plus 4 by 4, and this is given by e square plus e to the power minus 2 plus 2 by 4, and this is e plus e inverse by 2 whole square. This is equal to I plus delta square by 2 whole square. Why we write this? Because delta is this, so delta square, this is given by e plus e inverse minus 2. Okay, so delta square by 2, this is by 2 also, and I plus delta square by 2, this is plus I. So we get e plus e inverse by 2 from here, and we get by squaring both sides, this is square and this is also square. So we get e plus e inverse by 2 whole square. So we write this result here. Okay, this is the proof of relation number 10. 11, we write first the definition of delta, and this is already right here, definition of delta, and we take common from this relation delta. This is equal to, we take common e to the power half. So e to the power half into, this is I minus e to the power minus 1. And I minus e to the power minus 1, clearly from this relation, this is equal to nebula. So we write e to the power half into nebula, and this is given by nebula into e to the power half, because nebula and shift operator are commute, and this is given by nebula into e means I plus delta and to the power half here. So we prove the first relation, and by similar argument we prove all the 4 relation of 11 by using these 2 results and from this definition one by one. Okay, now we go to the relation number 12. Put first the definition of mu. This is given by this, so there is nothing to prove for the first part. Okay, now for the second part, we take common e to the power minus half. then we get half into e plus I into e to the power minus half, right? And now half into, what is the value of e plus I? Clearly from here e plus I means 2I plus delta, and what is the value of e? This is given by I plus delta to the power minus half. Okay, so we get this is I plus delta by 2 into I plus delta to the power minus half, and this is the proof of relation number 12. For relation number 13, we write first the definition of delta, and the definition of delta we already write here, and delta, this is given by, we take common e to the power half and getting the relation I minus e to the power minus 1. Okay, and what is the value of e to the power minus 1? This is I minus delta, so we get this is e to the power half into I minus I plus nebula. Okay, I cancel out, so e to the power half into nebula, and this is also written as nebula into e to the power half, because nebula and shift operator are commute each other. And similar proof is also proof number 14. Here we take common e to the power minus half. From this relation we get this is delta, this is equal to e to the power 1 minus I into e to the power minus half, and from this relation we write this is equal to delta into e to the power minus half, and since delta and shift operator commute each other, so this is right e to the power minus half into delta, and this is the proof of relation number 14. In relation number, this is not relation number 14, this is relation number 15. There are two similar type of proof. We prove here, and this is your home task. Okay. Now from the definition of delta we write this. Now squaring both sides of this definition, and we get delta square, this is equal to e to the power half minus e to the power minus half whole square, right? And from here we taking common as e to the power minus half, and this is e minus I whole square. Okay, so we get e to the power minus half into 2 outside of the square, and this is e minus I, so this is given by e minus I means delta, so this is delta whole square. So we get e to the power minus half whole square into delta square, and similarly we write this delta square into e to the power minus half square, this is equal to delta square. So clearly this relation is hold for k equal to 2, and by similar manner we get delta q, this is equal to e to the power minus half whole cube, sorry, this is minus half whole cube into delta q, and this is delta q into e to the power minus half into 3. Okay, minus half into 3. So we put, or we get the value or the relation for k equal to 3 here, and by similar manner we get this value for k equal to k or for any positive integer. Okay, by similarly we prove this relation, and this is your home task. Okay, thank you for watching. These are all the relation between the difference operators. Okay.